talk about the most recent developments associated with the use of high-index dielectrics. I'm at Australian National University. Also, I have a group at ITMO University, St. Petersburg in Russia, since 2010, when I got a grant from Russian government. First of all, I start from a very well-known topic, plasmonics. Plasmonics is a very active field with many promises, which is based on properties of so-called surface plasmon polaritones. It's a hybrid waves which are composed of electromagnetic radiation propagating along the surface between the dielectric and metal and free charges of metal. So this combined excitation near surface, that's called surface plasmon polaritone, with polaritonic properties, in short called plasmonics, was driven many ideas of so-called sub-wavelength photonics, when all these excitations and wall localization of field and different settings like here or there, or just localization near the metallic particles, are actually very, very much sub-wavelength. Their dimensions of these localizations much smaller than wavelength of light. Of course, this was driven many ideas to actually employ this surface plasmon polaritones for miniature devices and for nanophotonics. And that field developed for a number of years, and it got some connections to also independent development of field of so-called metamaterials. So metamaterials are artificially created structure which are based on local resonances. This resonances actually comes from electric dipole resonances similar to plasmonics resonances. So we excite separation of charges and effective dipole moment of electric field in such a metallic nanorod. And in addition to that, and that's associated with the word meta, we also excite magnetic resonances. When free charges oscillate in this split ring, then we create effective magnetic moment up or even down, and then in effective oscillations, we excite strongly magnetic component of electromagnetic field. Being combined in structures, these elements produce new type of materials. So materials which have different magnetic and electric properties on that plane of magnetic and electric constant epsilon and mu, which enter Maxwell equation, we basically can put any point and design such a structure. In short, from the very beginning, when pioneers of this concept created the field, we basically had in mind the following picture. So similar to nature, which make materials made of atoms, molecules, and different small objects, we create a structure which looks like a piece of material, but it's composed of many elements like that, which are much smaller than wavelength of light, which occupies several periods of such a structure. So that's why we call these elements meta-atoms. So we're much larger than atoms, but still much smaller than wavelength of light. And the properties of these materials can be engineered by dealing with these elementary units. So that field appeared around 15 plus years ago, and it was developing with many highlights and many media attention. So this involved, for example, optical magnetism, so magnetic properties excited for non-magnetic materials only due to patterning, negative index and clocking, possibility to hide object by making special type of clocks, optical circuitry, superlasing, hyperlasing, especially effective chirality. So many of these ideas, as you can see, through ages were developing in the last 15 years or 10 years, and currently we move to the new phase of active tunable and reconfigurable metamaterial. So it all sounds very exciting, but in fact there are very deep problems in this field. Why? Just this is this is example which show one of the applications of this metamaterials for enhancing of MRI resonance, which we suggested some years ago with my colleagues from ITMO. Actually, employing this metamaterial structure, we can enhance MRI resonance and even reduce time which patients spend in the chamber, which is very important for many people. About 10% of people can't stay in the chamber for a long time. Anyway, I just coming back to what I started to say, that this structure, this is a different example of the structure. This is more like hypothetical, but many of them also fabricated. For example, that one is a multi-stack dielectric, metal dielectric, what we call fishnet multi-layer structure. We all actually have as the main elements units which support dielectric dipole resonances, but in addition, they all support magnetic dipole resonances. For example, here metal, dielectric metal, in-plane oscillation, out of parallel and anti-parallel oscillation will produce two modes which are responsible for magnetic and electric moments. But if you look at these all structures, you see that we all have metallic elements, and we suffer from the same problem which we have with plasmonics when we try to apply plasmonic element broadly, because we have losses and heating and all this detrimental effect in these systems. So the recent development actually moved to the study dielectrics, and this even field which was created a few years ago was termed Mie-tronics by editor of Nature Photonics, and it's basically rely on so-called Mie resonances. Mie sounds like Asian name. Actually, there is a province in Japan, Mie, but it's actually Gustav Mie. It's a German scientist who, long time ago, more than 100 years ago, he solved Maxwell equation exactly. It's called Mie theory, and this Mie theory is given by explicit expressions for electric and magnetic field of scattering fields from this sphere. So he looked at the sphere, and currently we can program all this solution in Mathematica, but for physics it's very important to know that the different manifestation of the theory, a different effect described by this theory can be described as this dimensionless parameter. So this is the radius of sphere, it's the geometric size of the sphere, and this is wavelength. Actually, depending on the value of these parameters, we cover many interesting effects in physics, from Rayleigh scattering to geometric optics. So what is happening if you just look at the solution or just try to measure experimentally scattering of particles? We see that if particles are very small, of course, resonances which appear are dominated by plasmonics, surface plasmon polaritones excited at the surface of the sphere. If this silicon nanosphere made of such small nanosphere made of silicon, but being small, we do not see any effect in the scattering. But if I now increase size of this sphere, I observe a completely different picture. So all this plasmonic resonances become broad, but instead we see sharp peaks associated with dielectric nanoparticles. This is exactly what we called Mie-resonant Mie modes, and we are associated with a very simple physics condition. So wavelength of light inside of the particle, which is lambda over n, which is n refractive index, should be comparable with the geometric size of the sphere. When it happens, we see different peaks. So first peak, actually, it's magnetic dipole resonance. Magnetic dipole resonance is shown here, and electric dipole resonance appears like a second peak in this scattering cross-sections graph for silicon sphere. So basically, when this was discovered, people said, wow, we can make this metamaterial structures from dielectrics. And the entire concept appeared, and this concept was much broader, much deeper than plasmonics. Why? Because the structure here is several hundred nanometers, and it supports different multipoles, electric dipoles, magnetic dipoles, and quadrupoles, and make an interferer. This interference produces many interesting effects, so-called Kercher effect, unidirectional scattering, anapole regime when we suppress far-field radiation, phonoresonances when we have superposition of semaphore mode, a so-called bound state in a continuum. I will talk about them later. So there are many associated effects. I don't have time to talk today about this isolated nanoantennas, but I just mentioned that few examples of nonlinear Mie-tronic effects which associated with strong Mie resonances, like very efficient harmonic generation, third harmonic, second harmonic, then smallest dielectric nanolasers, room temperature, about 300 nanometer size of this cube, and even stimulated Raman scattering. All these details can be found in a very recent mini review paper published in ACS Photonics, not yet pages, but it's published online. I move to a very interesting field now associated with so-called metasurfaces. When we compose these elements on a plane, in the structures, there's a few examples of such composition, we come to a completely different concept. This concept was pushed forward by Federico Capass, one of the pioneers of several fields. In particular, this is his slide when he tried to explain how this metasurfaces works. So if you actually pattern or change structure of the surface, we can redirect wave in the different directions due to this patterning making the surface covered by resonances. This is similar to diffraction grating, but in fact it's much more general because it's introduced phase variation along the surface and modifies Snellius law by adding this possibility to actually redirect this reflection and refraction. So metasurfaces is a very powerful concept. There are many papers people publish on metasurfaces, and I believe today also will be another presentation from China about metasurface properties. But I just wanted to say that our strategy of my group and my collaborators actually employ multipoles for efficient transmission, and also employ a new type of resonances associated with bound state in a continuum. So I don't have time to talk about everything. I will talk about bound state in a continuum because this topic is not very well covered in optics literature and in optics studies. Bound state in a continuum comes from quantum mechanics. Actually, it was a paper published by pioneers of quantum mechanics in 1929, which introduced exact solution with these properties. To show these properties, I use a simple cartoon. First, standard situation from quantum textbooks, which present possibility to have extended quantum states or localized quantum states, which in spectrum correspond to continuum spectrum or discrete spectrum. So bound state in a continuum actually correspond to different situation. Imagine that we change our trapping potential well, so making this wavy tails. Then in this case, of course, we will have localized solutions associated with discrete bound state, normal bound state, and propagating state. But in between, we can look at the propagating wave, which will experience reflection and transmission. We can match phases in that way that we can construct solution which will be fully localized, even being above this cutoff of energy. So in reality, it will sit in a continuum spectrum, but it will correspond to localized solution. This type of solution will not very much interested for people because they assume that this solution appear under special condition, which is exactly true. But we are physicists and we are interested not in mathematical solution, but in a physics concept. So we basically use a solution to suppress radiation for this mechanism of suppression tail and achieve very high Q, high quality resonances. Just a few words that this type of bound state in a continuum became known in optics only in 2011 for a very simple experiment, and then it was activities in photonic crystal slab, and some summary can be found in the first issue of Optics Photonics News this year. Very simple physics behind these modes associated with possibility to couple two different type of modes here, propagating left and right. When introduce gratings, we actually couple them, create a band gap, and this band gap gives us two possibilities. With the two modes, right and left, we can compensate leaky modes and then create bound state in the continuum, or we may enhance leaky modes and create highly radiative state. So basically, we are dealing with solutions like that, which suppress leakage. If it's ideally, it should be suppressed completely, but not ideally, it's of course there is some leakage, but we actually control this leakage and enhance localization of wave. There are several types, generally 4 types of this bound state in the continuum, which you can find very often were associated with so-called dark states, dark mode, which are nothing but bound state in the continuum. And we employ it in our studies of different new metasurfaces and metamaterials. One of the concepts which people like very much associated with so-called symmetry breaking. If I look at the normally propagating wave on this two-dimensional array of resonators, then usually normally propagating waves do not couple. You need inclination to actually get matching and coupling to the modes. However, if I break symmetry in this element, I can couple due to symmetry breaking of this single element, radiation propagated normally to the in-plane modes. And this can be controlled by controlling symmetry. In fact, this is directly associated with bound state in a continuum, and we've shown in our theory paper that these structures all can be matched, described by one theory, matched in a single curve, and basically we can control both Q factor and the position of resonance by dealing with this type of asymmetric solutions. Currently, several groups pick up these ideas. There are hundreds of citations to that theory paper and many demonstrations. These are examples of these metasurfaces with asymmetry, also coming from my group. And currently, people who are interested in equality factors, so initially it was done without knowledge, and then it was in 18, it was a theory describing the structures. And now people, with controlling asymmetry, pushed the Q factor of the structures up to 18,000. This is a lot, actually, for application. If you go to applications, I will mention only a few because my time is running out. So one of the applications I like very much is for biosensing. For biosensing, we created pixelated metasurface. It consists of 10 by 10, 100 of different metasurfaces. This is a large element with a tilted bar. We allow to have a resonance. So pixelation means that we scale them. So we have an array of resonances like shown here. Now we can employ this metasurface for sensing in mid-IR by placing some substance here and watching absorption. And in particular, for each element, we can construct so-called barcode, which show you which resonance will be dominated and how actually these resonances will be manifested. And in fact, they can be traced without any spectrometer by just simple imaging. This paper was published in Science in the end of 18, but we then had a few developments, in particular going to hyperspectral biosensing with this concept and applying to many other problems. I just want to mention that we can control these resonances with a great accuracy. And this is example of chiral bound state in a continuum, chiral resonances of metasurface, which are composed of this a bit shifted elements, allows one circular polarization to go through, and with a very sharp resonance, another circular polarization will be reflected completely. So in that way, maximizing chirality in such structures. My time is running out, but I come to the final slide, which shows you that very big future in this field is actually to use hybrid structures, combine dielectric combined with plasmonics. Some ideas appeared a few years ago, and recently we demonstrated that in collaboration with a group of Bao-Hua Jie from Swinburne University. The structures made of dielectric and covered by very thin layer of metal, and such structures combine advantages of Mie-resonances and surface plasmon, and that may create a new design for advanced metamaterials. So as I promised, I come to the end of my talk with some summaries and conclusions. First of all, I try to explain in this very short time that the initial field of metamaterials created more than 15 years ago, still very active research, but it's now rebranded to fields called meta-optics and metaphotonics. We are no longer interested in average parameters. We study resonances, we study resonant response. And great advantage associated in this field is the use of high-index refractive, high-index dielectric materials, which supports Mie-resonances. Now it's time to actually employ metasurface ideas, metamaterials idea for creating specific devices. I shown biosensing device, which is currently very efficiently implemented and even used for some application. And this new physics beyond all this interesting development, behind all this interesting development is associated with interesting concept of bound state in a continuum, as I try to explain here. Thank you very much.